He's a senior cybersecurity research engineer at the National Motor Freight Traffic Association, NMFTA, and he works heavily with with embedded systems.
And they are expensive.
And expensive.
They are expensive.
Experience in embedded systems. And he's also a global speaker and DEF CON volunteer, so focusing on hardware and automotive cybersecurity. So then please give a warm welcome to Ben.
Thanks, Nils.
Thanks for having me here.
Here, I gave those to you and Eric. Would you like to pass these out? If anyone wants some sweets, just take one and pass it on. If you like sweets, they're Canadian maple syrup hard candies. So they're very sweet. So you have to like sweets, or else. I also have some stickers here. I know it's after lunch. Hopefully for involvement. If you're involved asking questions, I have stickers to give out, okay? Try to entice you to stay awake. So we're gonna talk about seed key exchange. You've already heard about seed key exchange. Everyone here probably knows what that is, but we found it in a really weird place. This is me. You gave me a good introduction. Thanks, Nils. Yes, I am posing for a glamour shot underneath a trailer because I'm weird like that. And there's my handles. I'm known as Static on my CTF team. Right, so this work could not be possible without the help of a lot of people. It's certainly not, like I'm here speaking about it in front of you. I'm not the only person that did this work. There's a lot of people to thank. I have a great colleague named Ann Zakos. I have a great input from Jonathan Mars. Some of you may recognize that name. I don't need to name where he works, but he's related. And some of you may recognize Tom Forrest, who gave me a lot of help at critical times. But most importantly, and this is the last one down here, the National Motor Freight Traffic Association, although it sounds like a government agency, is not a government agency. It's a trade association. We're made up of people that own and operate trucks, Class 8 vehicles. And without them actually letting me do the testing on this very expensive equipment, we wouldn't have been able to do this. So it's very key to thank them, and we're lucky to have their support. So we found seed key exchange. And where exactly did we find it? It was weird. If you look at vehicle dumps, if you do traffic analysis, you can look at this hex dump here, and you probably see it already. I'm trying to find my laser pointer, although you can see my cursor, right? Yeah. So if you look, you can actually see 2767, 2767, right? This is a seed key exchange. And in fact, on top of that, you can clearly see that, so it turns out it was KWB 2000, not UDS, but you can clearly see the ISO-TP layer there too, right? You have the size of the responses encoded in ISO-TP, and there's even a transport protocol. Now, the weird thing is where we found this was on J1708, which, how many people here are from North America other than me? Right. So in North America, J1708 is an ancient protocol for diesel engines, and it looks like RS-485, which is like a common mode wired serial bus at 9600 baud. That's what 1708 is. And what we're finding is that 1708 has this like data link escape system, DLEs, that let you tunnel proprietary messages inside 1708. So the next layer here is these something FE something. See, ACFE 89, 89 FEAC. These are point-to-point data link escapes. So we found data link escapes containing ISO-TP, containing KWB 2000 on J1708. But the weirdest part of that is that it was on a power line network that's emulating J1708. So it's just a ton of weirdness, right? So I found it on my bench. Here's a picture of a clean bench day. And the target is obscured or obfuscated by this monkey. Here's the target obfuscated by red mud, okay? The power line network that we're talking about is a connection between tractors, the power unit, the big thing that you see on your right, and the trailers. And in North America, this is the only way to show ABS fault information in the cab. I keep clipping your mic, I apologize. It's the only way to show fault information. So if there's actually a fault in this ABS controller, the driver knows because it's communicated over power line to their instrument cluster here in the cab. And there's no other way to do that in North America that satisfies the regulation. Here in Europe, you actually have a CAN bus that goes from your trailers to your tractors. And you have all kinds of features on that CAN bus, including trailer fault information. We don't. we have to get it over this power line. And that's true not just for like those box vans that you saw, it's also true for bulk haulers, for tanker trailers, okay? The reason the tanker trailers are relevant is the target that we found is supposed to be an advanced system that's only found on tanker trailers. So here's the power line. In trucks, we have two main networks. We have a CAN bus. I think everyone's mostly familiar with that. In trucks, we have a J1939, which gives us like extended identifiers, and there's a transport protocol, and there's other stuff going on, but it's basically just a CAN bus. Then we also have this power line network, and the power line network is just one segment from tractor to trailer. It's very slow. It carries only one mission time thing, the lamp failure. That's the only thing it's supposed to do. Suppliers have added a whole bunch of other stuff as value add, but the only thing it's supposed to do is that lamp. The lamp message tells you if there's an ABS fault or not. And then diagnostics get tunneled in this data link escape. The information you see on the right is trying to convey a whole bunch of technical information in one image. The J2497 power line protocol was implemented using a converter chip. One side of the converter chip reads and writes J1708, and the other side reads and writes this power line network. The power line network is done with frequency chirps, right? So you can see it's this 100 microsecond word that sweeps from roughly 100 kilohertz to 400 kilohertz. Those chirps get built up into a combination of an amplitude shift keyed preamble. I'm kind of like waving with my left hand and pointing with my right hand over here on this slide. And then it also gets stuck into this binary phase shift keyed body, and it's all chirps. So the whole signal just spreads the whole spectrum from 100 to 400 quite rapidly. And if you look at it in a spectrum analyzer or a waterfall plot, that's what you see. You just see energy right across the band because the message happens so quickly as it encodes it. And the encoding is of all these bits that you see here. And those bits map exactly to 1708. So the way this was deployed, the suppliers took 1980s microcontrollers that were speaking J1708 and they stuck a converter chip in front of it in 2001 when they regulated this. And so we have 1980s code on power line networks. Obviously, this supplier had gone and updated things because this is KWP 2000. They had a reason to change things, but it was still using the exact same stack that we just talked about. Right, so that's the power line network. The other thing is how we test this, okay? The Chuff test is what we use to confirm that we can talk to the brake controller. The brake controller in the trailer actually can control the solenoid. And if you listen, yeah. So the solenoid releases air pressure. I'll do it again. And the reason it's called a Chuff test is because of that sound, that also known as a solenoid test. The solenoid tests, when they cycle the solenoid, they actually drain air supply. The braking control in North America is all done by pneumatics. So it's a red supply line and a blue control line. And the blue control line is very low flow. That red supply line is very high flow. And the solenoid test actually dumps reservoir air. The tractor and trailer brakes in North America are spring brakes. So as you bleed air, you eventually fade brakes and then apply brakes, right? Because they're spring balance brakes. The whole point of the solenoid test is that it's very useful to confirm that a brake controller has received your message. So if you're testing to see if you can get a message to a brake controller, what's really great is to have it make some kind of a noise. If it makes the noise, you know that it received it. Right? We don't have to get on the bus and listen to the bus to see if it received it. We can just listen for the sound. All of this is abuse of existing functionality. No exploitation was done here at all. They designed the brake controller to receive this message and respond by doing a solenoid test. It's a valid diagnostic command. In this particular case, which is different than the first research we did with dry vans, you needed to do an unlock. You need to do seed key exchange to send this command, which is why I was looking at that diagnostic dump. I wanted to figure out how can I do these solenoid tests on this particular trailer. This particular trailer ended up being a demo event. So the marketing team in NMFDA wanted us to demonstrate this attack. And they gave me a tanker trailer to do it on, but we had never seen a tanker trailer before. So I had to set it up on my bench, and get this all set up, and then we successfully did it. But of course, to do this, you need to unlock seed key exchange. You need to authenticate yourself to the diagnostic stack. There's a lot of different ways to bypass seed key exchange. Some of you in the audience know all of them, and you might be familiar with most of them in here. This is an attack tree that I put together. I'm a big fan of attack trees. It helps me kind of organize my thoughts into these things. We suspected that because of how cheap this thing was in terms of like what electronics were in it, that it would have a time-dependent seed. And that it was worth testing to see just how time-dependent it was. If you want to look at all the different ways you can reset attacks, I do recommend the Sekar Kuhn-Lavel's paper called Candid. And of course, we're talking about a specific case of this 4.3, just retry. So if you were pen testing an ECU, some of you do that, how would you test for susceptibility to a reset attack? It's probably not the first thing you've done. I think, Jonas, I think the battery just went dead. Jonas told us. So this is down here?
You have to press it long.
Press it. Okay. So before lunch, Jonas told us about some of his pen testing experience using, HydroVision, Scapy, and there's a lot of different test cases that you might put together. One of them, like you said, Jonas, you capture a whole bunch of seeds, then you do some randomness analysis on it. That's definitely one way to look at susceptibility to the reset attack. But you might test other things, like you said, what happens if you send that 2904 certificate good first, right? That's kind of like, what if you just send a yes, I'm okay? Trying other things. You're not just going to go straight to timing susceptibility. And of course, you might use Karen Caribou, but who am I joking? This is ScapyCon. No one's going to use Karen Caribou here. We're all going to use Scapy, right? And Karen Caribou has this thing where it goes, fuzz, 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 calls the UDS fuzzer. And it says, I'm going to do a reset, and then I'm going to look at the seed. And if it sees any repeats of those seeds, then it's vulnerable. So the question is, like, if you don't see a repeated seed, right? If you dump all these seeds and throw them into the NIST standard test suite, but there's no repeated seeds, are you still good? Like, how do you decide if it's not repeatable enough? And of course, here's the Scapy version of Karen Caribou with a big fix me, right? The sleep that you would normally throw here in Python, even if you got pygame out and did like a hot wait with pygame, is still a pretty bad sleep. And the send p fast is a good option here. If it had like some way to do the interpacket timing, that would get even better. But timing dependence of seeds requires some determinism. And that's why you have iterations in Karen Caribou, right? When you're doing this with UDS fuzzing, I know ScapyCon, not Karen Caribou, but it has this feature where you just repeat, repeat, repeat. And if you repeat enough, you might see a repeated seed. And that's because of this non-determinism in the sleeps. So my situation with J1708 was a little bit worse. I didn't have Scapy yet. I do eventually get Scapy. I had this crappy Python tool that I wrote, J1708 send, and I had the bash terminal, and I just sent the reset requests and the seed requests, right? So if you look here, I'm doing an ECU reset, I'm doing a DSC, a diagnostic session control to 83. This is KWB 2000, not UDS. And then I'm asking for my seed. And I did this loop for a long time, and I just looked at them, and I did some, repetition analysis, and I found that, yeah, some of the bits would not change. Some of the bits were clearly time dependent. But I wanted to know how time dependent was it really? And the key point about this is that if you're going to test time dependence of a seed, you need to make sure that you're sending that seed request at exactly the same relative time from the reset every time with as little jitter as possible. And this is the stack that I was stuck dealing with. When you're dealing with truck hacking, you have to use these things called vehicle diagnostic adapters. And they're similar to like what you have in automotive with the J2354 adapters, except they're kind of crappier. They're just not written very well, and the DLLs are terrible. And you're laughing because I know some of the J2354s are like that too, although obviously some of the ones down the road are quite good. I didn't have any of the good stuff. I had this really terrible DLL stack. And the timing variability was really, really bad. So how how did I fix this? How did I get to deterministic seed tests? The answer is I didn't use this stack. I used something completely different. As a reminder, I do have stickers up here for good questions. And you can interrupt me for questions if you have questions. Okay. So the title is wireless and blind, right? What do I mean by wireless? What do you mean by blind? The wireless part is pretty straightforward. We had discovered in about 2019, 2018, just before the pandemic, that you could read wireless traffic from this link between the tractors and the trailers on this power line network. That signal that I showed you that chirps, it chirps from 100 to 400 kilohertz, and then they deployed this technology on giant pieces of metal. And they're not big enough to end up being like quarter wave resonators or anything, but they're still big enough to actually radiate that energy, and you can pick up this signal. We also at the same time discovered that you can write the signal. It just took a really long time to get that disclosed. So we got 2 CVEs for wireless. You can read remotely, you can write remotely. Again, none of this affects Europe. You're all fine. It's only a problem in North America. And apparently I'm the only North American here, so it's only my problem. But this can happen, okay? That's the wireless part. The blind part is kind of like a hard mode restriction. We do like a challenge, but we also know that suppliers pay a lot more attention to things that are cheap, right? If you go to a supplier and you say there's this vulnerability, but like you have to use this specialized equipment and it costs a couple $1,000s and you have to like have intent, they're just not gonna care. They have many other things to worry about when they're putting these pieces of equipment together, these boxes together. It's much more impact to get something fixed if we can show that it can be done with like a very cheap piece of equipment. And it turns out there's a really cheap piece of equipment that could transmit this J2497. Just because we're doing this blind does not mean that you have to do it blind. It's completely feasible to create a full duplex radio system that reads the traffic and sends the traffic. We just demonstrated that you could do this without making a full duplex system because it makes the cost of the attack much lower, and it means that the attack feasibility should be much higher so people will pay attention. The limitation here is, if you're doing this blind, all of your delays have to be set up just right. You have to tune your delay so you hit these gaps in the traffic and then put your messages in there. So it makes it a little more difficult to put together the payload. So here is an improved blind unlock, still using Scapy-automotive, and still the fix-me's, right? Like, you could conceptually say that I'm gonna send this reset and I'm gonna do my DSC and then I'm gonna ask for the seed. And if I know exactly what the seed is that comes out every time, then I can just send the key. And these sleeps will be fine except for the jitter in those sleeps. So I need to fix this jitter problem. How did I do that? Well, we're talking about a wireless system. So I use software-defined radios. In software-defined radio receive path, you have all kinds of stuff like bandpass filters, preconditioning amplifiers, you name it. But for transmit, SDR transmit's really just a DAC. And you just shove numbers into this digital analog converter and it just streams the data out. And if you're getting really fancy, you might have a filter and an amplifier over here, maybe. But your determinism is really high because the clock of this DAC is a sample clock, right? So it turns out that you can also get these things for really cheap. This is an FL2K VGA adapter. The VGA adapter was implemented in software in a driver in Windows, and it just creates an entire frame buffer and then bit blitz it out on this adapter, which means it also is valuable as an SDR transmitter. And the FL2K can be used to transmit any radio signal from baseband up into like the gigahertz range, which means it's perfect for my application because I needed a baseband transmitter and it only cost 25 bucks. So this is what the stack is that we use to test the determinism. We use FL2K TX, which is a user space application. We feed it with a bunch of data. There's some user space stuff that happens, and then down here in the SDR domain is just a big buffer that just feeds the data out. Now there's still some other sources of latency here, like those converter chips on the receiving side do have some service latency, and then the software has some service latency as well, but which has jitter. The latency has jitter. But for us, we almost completely eliminated the jitter because we weren't using the weird DLL stack anymore for RP1210. So that's how we tested determinism. And then it came down to a question of like, how predictable is predictable enough, right? So if I'm gonna do this blind attack, I want it to be feasible. So I think like trucks stop at red lights or at stop signs in the order of like a minute to 2 minutes. They're kind of like slow to get going. So if I can have a 2-minute window, how many attempts can I do at that time? So if I can get like to 30 seconds per attempt, probably for this thing, because I know how long this ECU takes to reset, about 6 seconds. I reasoned that a 25% chance of seed control would be good enough. Then I would get 1 in. Now remember, I'm demonstrating through abuse of commands, but that doesn't mean that I couldn't also be cooking up some kind of a payload to send in and take over the ECU and other means. I'm just confirming that it receives my messages by using this abuse of commands with Chuff. So 1 in 4 chances, 30 seconds per attempt in a 2-minute budget seem pretty reasonable from a making really bad things happen kind of point of view. So we set that as our goal. And how we did this was we treated the development of this payload, the timing of those delays, like a glitch campaign. All right, you have all these parameter sweeps. We're sweeping the parameter space of all these different delays, trying to get our message in just the right spot. And I didn't have a really nice like chip whisperer like setup for glitching because this is an SDR transmit with a ECU on the bench. So I cooked up some custom SideRock decoders to look at the output on the power line so I could get this nice little transition from purple to green you see down here. So this is an example of where a particular parameter sweep goes from like the nothing worked to the yeah, things worked. And then I can count the number of times and I know where the parameter switched over and then I can tune my sleeps. So this is not the subject of the talk, but that's how we did it. This is what it looks like if you're gonna do this actual attack using the FLK SDR. This is based on the code that we published for the mitigation called the J2497 keyhole mitigation. That mitigation code is actually a valid transmitter. So you just repurpose the mitigation to transmit the malicious signal. And this is the win screenshot. So this is where we actually got repeatable seeds down there by tuning all these things and sending all the traffic. And it turned out to be, if you're doing 30-second attempts back to back to back, you can get the seed you expected 50% of the time, which is not great, but still meets the win criteria. The one that's crazy is if you let the brake controller cool down for like 2.5 minutes and then try, that first try is greater than 90% chance of the seed that you wanted. So it's more than likely that, you know, in this scenario where the truck drives up and stops, the attacker's first attempt to get a seed out is gonna be the one they expect, right? Which is fine, we're okay with that as an attack. So this is the timeline. The vendor did confirm that there is a chance of software corruption with the attack because we are doing a diagnostic unlock. So we have all the capabilities that the diagnostic tool has. And it also had a security advisory from CISA issued at the same time. So the problem with the reset attack is super cool. Everyone loves influencing seeds, but you still need a matching key, right? Like, okay, I controlled the seed, how do I unlock it? You have to match the key, you're not done. But there's lots of different ways to get a seed key pair. If you have the diagnostic tool, you can just get lucky and see the key come out that matches the seed. That happens more often than not. You might need to build a big table of them. So like loop the software around and around. And ultimately, that is what we did. We made an auto hotkey script that goes and like clicks the buttons in the diagnostic tool and just keeps like trying the thing. If you're close enough to actually see the video, you can see that this video is very silly. It's not the real tool. And we got the seed key exchange pairs. You can see them over here on the left. Now, if you do this stuff all the time, you probably can look at that scatter plot and say, but wait, there's more. That scatter plot is hella weak, right? Does anyone know how weak that scatter plot is? No? It is linear, right? And you can confirm this by using Z3, which is like a satisfiability solver. And you take those pairs, input and output, and you just tell Z3 you want to do some 16-bit math that's y equals mx plus b, and it says, yeah, you're good. That's a linear key routine, right? Not great, but also not surprising if you're in the industry. Right, so we had the diagnostic software, that's one way to get the matching ones. We had captures, that's another way to get the matching ones. It turns out that you could have reverse engineered the DLL inside the DLL, there was a function that was roughly called calculate password, and the function was right there. Or you could solve for unknowns, which is what we did with Z3, the two unknowns, M and B. We got them. Okay. So we unlocked it. We're good. So now what could we do? So this is the Scapy part. Thank you for paying attention up until the Scapy part of the talk. Can you retry key attempts? Yes, in fact you can, and here's the Scapy code that does it. Right, so we construct these UDS requests. We set our diagnostic session. Remember, this is KWP 2000, so we did it at 131. And then we get our access type, and when we send the wrong key and just confirm that we get a failure back, and then send the right key and make sure that it then fails. And I gave it away, but this SR1 hard fail is actually Scapy. Now keep in mind, I'm communicating with this ECU over power line on my bench. How many adapters for power line are in the Scapy tree? 0, right? There's 0. So here's the weird stack. So we put Scapy-automotive on top of Python CAN. So what? Everything's on top of Python CAN, I know. But we put that on top of RP1210, but not the CAN side of RP1210. We put it on the J1708 side of RP1210. And then we pack that into J2497. So we're using the weird RP1210 DLL that's interfacing to the 1708 interface, that's interfacing to the power line network, and then we're faking CAN. I'm gonna not go to the next slide. I'm gonna go back to the first slide for 1 second. Note here that each one of these messages is a 7-byte CAN message packed inside the DLEs. Not 8 bytes, it's a 7-byte CAN message that they packed inside the DLEs, which means I have plenty of room to just fake a CAN bus here, which is what I did, right? So this stack, we made a custom bridge that makes a fake Python CAN bus. And I hope people like Monty Python. Here's a little Monty Python joke for you. Yeah, 10%, I'm okay with that, I'll take it. So the driver code is really quite simple. We have these data link escapes, AC, FE, 89, 89, FE, AC, just like you saw. And when the API code wants to send a message, it just puts that data link escape in the front of the data and then goes down into RP1210 and sends it. Over here, it's receiving all kinds of data, and when it sees whether things are going to the trailer or back from the trailer, it fakes the 71, 79 diagnostic CAN IDs, and then stick the data in there. And I know it's dumb, but it works, right? And if it works and it's dumb, it's not dumb. Which means we can get cool stuff like this, which I think you're responsible for these graphs, Nils? Yes, so these are awesome. I love looking at these state transitions, and the first time I was able to like make that weird stack and generate this graph, I was very excited. After I looked closer and I was like, oh, it's fully connected, then I was less excited, but it still was fun to get the graph. So we just used UDS scanner, right? This is the Scapy UDS scanner class that you and Enrico Pozzobon put together, right? Somewhat. And we're not doing anything special with it. We're passing a diagnostic session enumerator to it, and we're using it kind of like out of the box. And the weird part is just that whole stack of software for the drivers. And we can also enumerate the security levels, which again is right out of the box Scapy code. Here we pass the SA enumerator. We're dealing with this power line network, 9600 bits per second ECU, so we have to have some kind of bigger timeouts. And this busy return code feature was really helpful because that was, if you don't set true here, you get all kinds of false positives. I'm also doing the wrong scan range. So you'll see like these conditions not correct in the table, and that's because I'm dumb and I'm not skipping the even parts of the services. If I skip the evens here, you wouldn't get those bad conditions. But this is just a like a markdown table rendering output from the output from Scapy. So it's just straight out of the Scapy code. And it lets you do all kinds of useful things to understand how do these ECUs work in like an interactive exploratory way. We also knew the seed key routine, right? There's an M and a B, which I've redacted, although you can reconstruct them with 2 captures, so you can have fun with that. And you can reuse the SA XOR enumerator, which I don't know if you intended it that way, but I can definitely monkey patch it this way.
It's intended.
It is intended, nice, excellent. And I was also able to capture a KWP 2000 special feature If it sends you back the seed 0000, that means it's already unlocked, which is handy to be able to detect as well. So you can just monkey patch the XOR enumerator as intended, now that I know, and you can enumerate what other routines can be unlocked this way. Okay, and I don't have the output from that. The output is nil. So the only thing you can unlock with this particular seed key routine is this diagnostic session. All the other sessions are not unlocked by this, which is good news for the world. What about service availability? So this one, I think there must be a better way to do this, but I enumerated what services are available, what diagnostic sessions are available, and then I just set up the reset function to unlock the ECU. I don't know if it would have been more complete to like reuse that XOR enumerator, because I think Scapy would have tracked the state change of the ECU as it went into the unlocked state. Okay, so I could have done this one better. The answer from this output is the state, the number of services don't change. It's the exact same services before unlock as after unlock, which means the ECU is doing its authentication checks like later on in the services, right? So what does this unlock get an attacker? Well, it's a diagnostic session unlock. Here is a table of all of the different diagnostic commands that the tool, the Windows tool, uses in its actions. You can see the heavily most used, which is also not surprising to anyone, is routine control. It uses a ton of different routine controls. So if the service availability doesn't change when you unlock the ECU, obviously something deeper in the sub-functions is going to check for authentication. So why don't we look at that? So what we did here was a switch away from Scapy, but we unlock the ECU and then we do another scan. The reason I had to switch away from Scapy in this case, and this is something that I would love to fix, but as I mentioned when I ask a question, I'm bad at Python, and I'm a huge fan of Scapy, but I haven't graduated to the like helping with Scapy level yet, so sorry about that, Philippe, but I do really love it. Thank you so much. There isn't any support for this weird return code request correctly received but response pending. And I haven't seen anywhere other than in this trailer. I mean, maybe it happens in other ECUs, but on this trailer, every time you asked it to do something that was going to take a minute, it would send back 78. And I had to do this really dumb thing where I close the iSoc, and then I just hot loop on the CSoc waiting for the response to come back. And I don't know how well that would work anywhere else, but on this particular setup, it was fine to just close the iSoc and then hot loop on the CSoc waiting for the response to come back and then stick that response back in there and proceed. But this is my terrible handling of hex 78. And I know it's ScapyCon. I wanted to show you my terrible non-Scapy code as well. When you do this, you do learn that several of the sub-functions do need authentication. And that's where the authentication is. So that's the segue into the modern attack surface, right? We made a really weird write-only SDR transmit of this seed control, okay? But remember, we could have done full duplex. It's obviously very easy to unlock these ECUs. It's just linear, and getting those two coefficients is not hard. Access to this bus is not limited to the wireless access that I would do with SDRs. In the modern world, today, people are deploying telematics devices onto the Powerline network. There's 4 different providers that make internet-connected systems that can also read faults from the trailer brake controllers. And just like on CAN bus, there's no read-only CAN access on the market. I mean, like data diodes exist, but people don't deploy them. In Powerline, there isn't even such thing as a data diode. This stuff leaks everywhere unless you specifically filter for it. So we're talking about internet-connected devices, you know, made to the lowest common denominator, reading these brake controllers that have the ability to dump air supply pressure and maybe more. I mean, we're just talking about command abuse. So there's definitely the risk here of that particular diagnostic session unlock leading to other control of these ECUs. And this is the same story that we all know about from, you know, the CAN bus in the tractor. It's just also happening in the trailer. Nothing anyone doesn't already know. So the CVE does have some impacts, but it's not terrible news. This is a good news, bad news story. So the good news is that, as I mentioned in that XOR monkey patching, that particular routine is not used for anything else on the ECU. That routine unlocks the diagnostic session. It doesn't unlock what is probably bootloader and the other one, which is probably engineering. Those don't get unlocked by it. Everything is all fully connected, so there's no like special path to take, which is kind of the bad news. It's all, you can go from one DSC to the other. The other bad news is that that particular seed key routine that we talked about, linear, is enough to command the diagnostic control. So I can dump air supply from the solenoid control just with that command, which is bad enough. And in the disclosure, the supplier did confirm that this particular unlock could lead to software corruption. So the really good news, like why we're talking about this at all, is that even though we can control the seed, right? We know exactly where to put our delay to get a predictable seed. We did find that there is some like serial number seeding across the units. So if I had two units side by side and I sent the exact same working signal to the two of them, the seeds that are coming out are the same over and over again, but they're not the same across the units. This is the really good news. So it means that this attack would have to be like a targeted attack. It doesn't scale to infinite number of units. Good news. But it might not be entirely useless to attackers, right? Like obviously a targeted attack, sure. I don't think anyone's going to defend against that. But we're talking about a 16-bit seed key exchange. And these things cost like $3,000 a pop. And we don't have the resources and time to go and test the entire supply. Obviously, the person that made this thing has access to the source code and can confirm, you know, how diverse the first seeds are. We don't really know. But even if it were diverse, there's way more units on the road than there are possible seeds, right? So it would have to be perfectly uniform in the space, and then it would still make it less than ideal in terms of like guessing the seed. So it's not perfect, but it's definitely better. Okay. And remember that you can make full duplex wireless systems. Those are completely technically feasible, and a telematic system could do this as well. And we're not just breaking stuff. We split our time between breaking things and fixing things. So we spent a lot of time in ATA-TMC committees, which is a North American Trucking Association committee for technical standards, advocating for deprecation of the power line network in the next tractor-trailer interface. We also spent a lot of time in SAE, truck and bus committees, trying to get the actual mitigations that have been published into that next standard, as well as recommending no one uses it anytime in the future. All that's published. Conclusions. I hope I showed you that timing-based attacks are generally applicable. I hope that you will think about managing your jitter budget if you're trying to estimate how predictable seeds are. I hope I convinced you Scapy-automotive is awesome. You probably already were convinced of that because you came here. And other stuff. And there is the white paper right there. So I showed you code snippets. The code in full is all available on the white paper if you want to run my crappy Python code, but you've been warned. Thank you very much. I think there's a question in the back.
Thank you very much for this great talk.
My pleasure.
Did you try dumping the software to find the relationship between the seeds and the serial numbers, or any other relationship?
No reverse engineering was performed in this project. I love RE, and I would love to have that excuse to do it. It's just so expensive in terms of time allocated. So we did not. We rely on the supplier to do that effort. They have the source code. Actually, and also good question. Nils, can you hand out things for me? Here, give that to the good question askers.
Okay.
Thank you. Sorry, go ahead.
Yeah, thank you for the talk and for the candy.
You're welcome.
I wanted to ask, maybe you said it and I didn't catch it, but what is the delay? Like, how often can you try this attack?
Sure. Yeah, so my budget was 30 seconds, but we can do it in a loop of about 18 seconds. Where's my my plot? There you go. You can see the time scale here.
So is this budget, when you say budget is 30 seconds, you mean that one attempt of the attack takes, is there a way to accelerate it? Like, would it be able to basically flood with the SDR and basically do it fast enough that you can almost brute force, or at least try many possible combination of seed key? Like, since you said that it's only 16-bit and not even all of those 16
so how could we just burn through it faster? Enrico, are you Enrico Pozzobon? It's very nice to meet you, sir. I like your work. Okay, so you're asking a really good question. I don't have a great slide for this, but you can see this curve on the power line plots here. Essentially, we tried to send a message into the controller as soon as possible after reset. And the good news was we found that it would actually reply to the message about 7 seconds later. So there was a window 100 milliseconds after reboot where we could put a message into its buffer, and it persisted it all the way until it finished its initialization in 7 seconds. And we were like, yes, 7-second attempt is fantastic. The problem was, even though it would say, yes, I did the DSC, I want to switch to DSC 83 first, it confirmed that. The UDS stack completely forgot about it right after that. It was a you got burned moment. Yes, we'll do it, and then it just reset its state right afterwards. So we're really bound by this whole setup process that it does, and it tests its solenoids and stuff, and then it has a UDS stack that's accessible to us at about 12 seconds up. And then we have to wait for the right window, and then we can send our thing, and it takes to 18 seconds was the shortest we could get it for this one. But because we're using SDRs, when you're doing fuzz testing, you can just flood it. And we're able to fill the J2497 bus way faster than any of the diagnostic adapters can, because it turns out the preamble is completely ignored. It doesn't need to exist. So you can just send body messages back to back to back with just enough bit timing, and you can fill the bus with 2497 messages. So that answered both your questions in bad ways. I apologize.
One comment: if you need more time, just don't wait at a red traffic light. Wait on a highway, at a gas station or something, and then you have more time. But one question, completely unrelated: are you aware of any initiative to secure the general communication between truck and trailer? Because that is something that really concerns me, as you will know.
Very good. So last question first. The SAE Truck and Bus Committee, which is it's an international standards body that is going to be specifying our next generation tractor-trailer interface. They are working on exactly this. It's not just what the connector is, what the electrical properties are, but also what is required of gateways that'll be present on both sides. You already have a DIN standard for your CAN-based gateways from trailer to tractor. That DIN standard doesn't have any cybersecurity in it. And I think everyone that I've ever talked to in the industry recognizes that, we need confidentiality on some messages, we need integrity on pretty much everything, and we need to have preservation of availability on the tractor from the trailer and vice versa. So the SAE Truck and Bus Committee should have that in hand. The neat thing about SAE, and throwing some homework on you, you don't actually have to be an SAE member to participate in meetings. You do have to be a member to get the documents, do the voting, all that stuff. Literally anyone can show up at an SAE meeting and contribute. So you are welcome to attend those. I know the time zone might not be ideal for you. Your first question, you can put all the equipment necessary to transmit this stuff in a garden trailer and drive alongside things. You can do it. One, you'd be very conspicuous. You would look like you're doing some bad stuff. But the other thing we notice is that these are all ABS trailer brake controllers, so they have wheel speed sensors. They are all internally able to distinguish when they're in motion versus when they're standing still. And every single one we've seen so far correctly rejects diagnostic commands while it's in motion. I'm a good news, bad news guy. There is one exception to that. If they have a wheel speed fault pending, then they don't trust their wheel speed sensor and they will receive diagnostic commands while they're in motion. Good news, bad news. Thank you.
Hi, thanks for the talk. I wanted to know if you would be interested by a function that would enable you to send packets at very precise time slots.
I'd be happy to test it out for sure.
Okay. then I'll give it a try.
Oh, okay. Thanks. Feature request inserted. Thank you.
So you said in one of your slides you have a 90% probability after 2.5 minutes.
First seed, yeah. The first seed out is 90% predictable.
So have you looked at some side channels here? Is there some 8-bit counter running into some boundary or something
Like,
that?
what is the nature of the bits? Yeah, some of the bits are really static. So even when I did that bash script based version, so this completely bullshit test, where this is a bash script invoking the Python functions, Python like main scripts, I still saw some bits that were kind of static. So it's definitely timing influenced, but it's also like not clearly a linear function shift register either. Again, I didn't do reverse engineering, but some of the bits are quite static in it.
It's like it.
Yeah.
Okay, thank you.
You're
Great
welcome.
talk.
Thank you.
More questions? More questions? No? Then
Thank you so much, everybody.
Thanks again. It was a pleasure to see Scapy code on screens.
Yeah.
Awesome.